Hello, everyone. Welcome to the Guaranteed Safe AI seminars. I'm Orpheus, founder of Horizon Events, a nonprofit agency focused on AI safety R&D facilitation. The purpose of the monthly series is to facilitate progress in the Guaranteed Safe AI research direction. The session is 1 hour sharp, usually half presentation, half Q&A, and discussion. Today's speaker are Xuan. I'm sorry,
Xuan.
I've
No
Xuan,
worries.
Xuan.
Yeah.
With the topic engineering rational cooperative AI via inverse planning and probabilistic programming. Xuan is an incoming assistant professor in the National University of Singapore's Department of Computer Science, with a joint appointment at the A-STAR Institute of High Performance Computing, PhD in the MIT Probabilistic Computing Project, and the Computational Cognitive Science Lab. In terms of Q&A, we have a preference to have the questions at the end. So with all this, thanks so much for being here, Xuan, and the floor is yours.
Yeah, thanks so much, Orpheus, and thanks everyone for having me here today. We'll see how much time we'll have for Q&A. Hopefully we have, at least 15 to 20 minutes. I'm not sure I can give you all half. But yeah, excited to tell you a little bit about the work I've been doing on engineering rational cooperative AI by inverse planning and probabilistic programming. So, just to start off motivating the talk, humans, cooperate with each other every day in order to achieve all sorts of tasks, right? So whether it's a construction team working on a building, two developers who are pair programming, co-pilots flying an aircraft, or a group of scientists doing research together, we routinely exercise what you might call our cooperative intelligence, using our understanding of other people's goals, intentions, and actions in order to work together fluidly to assist others when they need help and to accomplish shared goals that none of us would really be able to accomplish on our own. And in fact, our ability to do all of this starts from a very young age. In this video, I'm going to show you here, this 18-month-old toddler is watching an adult do something quite strange. He's carrying this stack of books and repeatedly banging them into the door of his cabinet. And yet, without ever having been taught, the toddler figures out the adult probably wants to put the books inside the cabinet and automatically. So they're not taught this ability to do inference and assistance. They just kind of do this from a pretty young age. So what is it about humans that we are so cooperatively intelligent, even at this age? And how can we build AI systems that are just as cooperative? After all, the ability to understand, predict, and work with other agents is a key requirement for many AI applications, especially those that we want to make sure are safe. For example, it's a crucial aspect of building collaborative robots, which have to infer the subtasks that humans are working on. It's important for self-driving cars, which have to predict and coordinate with other road users. It's also needed by virtual AI assistants, such as Godot Clippy from Microsoft Office, along with its spiritual descendant, Microsoft Copilot, right? So both these systems have to infer what the user wants from their actions and explicit instructions in order to actually be helpful. And in fact, I think it's fair to say that the most recent wave of AI systems that everyone's excited about, so-called AI agents, require this cooperative ability as well. Whether they're helping us to write code or do online shopping, they had better understand our actual goals and reliably achieve them if they don't want to cause serious problems like they almost did for this journalist here, right? Basically tried to sort of place his booking for an expensive parking lot without ever checking with the user that that's actually what they wanted. So how can we build AI that cooperates with humans as reliably, safely, and efficiently, at least as well as humans do, hopefully even better, right? Well, in this talk, I'll be telling you about an approach to the challenge that we're starting to call rational cooperative AI. And this is a new term we're kind of workshopping. And roughly by rational AI, I mean, sort of old school notion of what AI was supposed to be in some ways, like AI grounded in explicit probabilistic modeling, inference, and decision making under uncertainty using coherent models of the world. I think rational and reliable in the way that many humans are at our basic everyday tasks, not rational in the sense of maximize utility globally over all possible worlds, but rational in this sort of very basic sense. And by rational cooperative AI, I mean rational AI that cooperates by having coherent models of other agents and reasons with and about them towards cooperative outcomes, right? How do we build such AI systems? We'll start with modeling other agents in this talk, also known as theory of mind, right? The ability to infer goals, intentions, and other mental states by inverting a model of how humans or any agent plans in an approximately rational manner, right? So this capability is required for all other aspects of human-like cooperative intelligence, and one could argue rational cooperative intelligence. And to show that we can scale this capability, the first half of this talk will be about sequential inverse plan search, or SIPS, an inverse planning architecture I've designed for real-time open-ended goal inference, right? So to achieve this kind of real-time performance, SIPS is built on two core technologies I've worked on over my PhD: probabilistic programming, a platform that enables scalable probabilistic AI and coherent probabilistic modeling of the world, in the same way that PyTorch really enabled deep learning to scale. And model-based planning. And both these technologies I've tightly integrated together in order to achieve this SIPS-style system. So together, these platforms allow us to scale inverse planning to complex environments with hundreds of possible goals, something that wasn't really possible before. Building on this central capability, I'll next show how we can develop model-based AI systems capable of cooperative communication with humans, the ability to understand the shared goals that underlie what we say to each other, and cooperative decision-making, the ability to coordinate on joint goals and plans, right? So to do this, I'll introduce an extension of SIPS called CLIPS, which achieves goal inference from natural language by using large language models inside of probabilistic programs. So this enables AI assistants to pragmatically follow instructions via cooperative planning and provide uncertainty-aware assistance to users even when their instructions are ambiguous. Finally, I'll end this talk by charting out a vision how we can continue scaling this rational approach to cooperative AI to the real world by using the capabilities and engineering platforms I've introduced here. I believe it'll be possible to build a new generation of cooperative, rational, model-based AI agents, including AI copilots, smart NPCs, collaborative robots that avoid the failure modes of current generative AI that will hopefully be sort of safer by design and also economically competitive with them. And in addition, by advancing the fundamental science and engineering of cooperative intelligence, I believe it will be possible to scale not just AI agents that cooperate with individual users, but also design cooperative AI infrastructure that enables humans and AI to flourish with each other despite our divergent interests. So that's an overview of the talk. And let's get started with how we can scale this agent modeling or theory of mind stuff. So suppose you're watching an agent in the environment I'm showing here. So given the initial state of the environment, a sequence of actions that an agent takes over time and a set of possible goals, we're going to focus on one aspect of theory of mind, which is inferring goals, right? And the online goal inference problem is to infer a distribution over the set of goals at each time step t. And ideally, of course, we like this to occur accurately, efficiently, and with appropriate amounts of uncertainty so the AI systems interacting with another agent, can navigate these cooperative scenarios in real time. We would also like to use a general approach that works across many different environments and domains. So for example, people have tried to do this in settings with many more possible goals. In blocks world, for example, a goal might be any block tower. You can spell out with an English word. So that's an interesting example of how quickly the goal space explodes, even in these relatively simple environments. And here I think the word drains is being spelled. And you might want to do this also in home environments where goals are basic household tasks, like setting the table with plates and glasses. So how can we scalably solve goal inference problems like these? Well, one approach that will be popular these days is to simply treat goal inference as a prediction problem or a machine learning problem. If you can collect a large enough data set of initial states, agent actions, and goals, then in principle, you should be able to train some classifier like a neural network or transformer to predict goals from states and actions by maximizing the log likelihood of that data set. Right. And if you try this approach, like I did with this particular neural network architecture here on about 4,000 action sequences, you'll likely find that on the training set, it does reasonably well, right? So here, when the agent goes to the bottom right, the neural network predicts that the goal is either the blue or yellow gem. But when the agent walks, up and to the left to get the other key, it becomes clear that the agent's actually trying to get the blue gem, which is unlocked, which is locked behind 2 doors, right? However, once we go to a test set example with a different layout, issues start to arise, right? So in this example, this red gem over here is blocked by 3 doors. And so if you see the agent go left to pick up the key over there, again, you need, keys disappear in this world once they're used. So you can infer that the agent needs 3 keys in order to pick up the red gem. So if you see the agent go to the left, it should be very clear early on that a red gem is the likely goal. But our neural classifier, upon seeing this, generalizes very poorly to this example, wrongly predicting that the blue gem is the goal for almost all time steps. And overconfidently too, because if you thought the blue goal was the gems, like why didn't you think the yellow one was too? Right? The blue gem was the goal, right? And in fact, test set accuracy is so low, it's worse than chance in this case, in this setting, even though we selected hyperparameters that performed as well as possible on a validation data set. So it's quite hard to get these neural networks to generalize. Plausibly, you need a lot more data or architecture with stronger inductive biases. And even so, we have no guarantees they would generalize correctly. So what's the alternative? In our work, we take a structured model-based approach, a rational approach, known as inverse planning, right? Rather than learning to infer goals from tons of data, we're going to model the agent as having some goal given the environment it is in, and that it takes actions by planning approximately rationally to achieve that goal. But we can't observe goals directly, only external behavior. So we have to invert the model, inferring a posterior distribution over goals that best explains the actions the agent took, right? Of course, this is just a high-level framework, and to actually do inverse planning, we need to make specific assumptions about how agents plan. And one standard set of assumptions that people have used widely is called Boltzmann rationality, which says that agents are more likely to take actions that minimize their cost of reaching the goal, also known as this cost-to-goal function or the value function, right? And this assumption is widely made in methods like inverse reinforcement learning. And in small enough environments like this grid world with no doors and keys, it's possible to compute this cost-to-goal function quickly enough that we can perform online inference. So for example, here I'm showing the cost-to-goal functions for each goal here computed via dynamic programming over the entire state space. That's the one for the red gem, the yellow gem, and the blue gem. Because we can compute these cost-to-goal functions, we can compute the likelihood of taking a certain action in a certain state, and we can just apply Bayes' rule directly and repeatedly to infer a distribution over the agent's goals over time. And you can see it's doing this very natural thing of inferring that at first it might be red or yellow, then eventually it's yellow. Unfortunately, the standard approach suffers from 2 key scalability challenges, right? So the first is that planning itself is generally intractable, right? So it's intractable in particular to compute this cost-goal function for most compositional planning problems, like grid rows with doors and keys that already is actually NP hard, or pick-and-place problems like a blocks world. And this is made worse by the fact that, at least traditionally, people would often compute this function via value iteration over the entire state space. Or if you imagine training a neural network to do this instead, it needs to have a good approximation over the entire vast compositional state space, right? So unless we have some magic way to compute this cost-to-goal function very quickly, Boltzmann rationality is just not, traditional Boltzmann rationality is just not going to scale to these more complicated environments, especially if you want real-time speed. And the second challenge is that inference is generally intractable, right? So part of this follows from the fact that, the planning part is intractable, so computing these likelihood functions is intractable when you're doing Bayesian inference. But also the space of possible hypotheses, like the agent's goals or plans, could grow exponentially, especially in open-ended settings like block words, this blocks world setting, where a goal could be any English word, or home environment where a goal could be any household task. So how do we address these challenges? Is it possible to still take a model-based rational approach at scale, or do we have to go back at machine learning instead, right? So I think a lot of people think it's not possible. We have to use machine learning. And here's where, our, different answer comes in. Here's where our probabilistic programming architecture comes in, called Sequential Inverse Plan Search, or SIPS. At a high level, SIPS addresses the first challenge by modeling agents as boundedly rational planners. Agents that alternate between planning ahead for several steps and acting. This is not only much less costly than full horizon planning, but also more cognitively realistic, allowing us to capture human-like mistakes from not planning ahead enough. And we implement this using a platform I wrote for high-performance planning called pddl.jl, integrating it inside of a probabilistic programming framework to create a probabilistic agent simulator that's both efficient and domain general, and we can use that to do inference. And to address the second challenge, SIPS performs inference over this agent simulator using a technique called sequential Monte Carlo, also known as particle filtering. Right? So instead of trying to do exact inference over all possible goals and plans the agent might possibly have, SMC approximates the Bayesian posterior with a set of weighted particles, which get updated over time. And this is a strategy that, I think there's good evidence to show that humans are using something like this when they're being approximately Bayesian about uncertain things they're uncertain about. And to automate all the math required to implement this custom SMC algorithm correctly, SIPS is written using this probabilistic programming library I wrote called Gem Particle Filters, which enables you to write these algorithms much more efficiently without worrying about the low-level details. So there's a high-level overview of SIPS, which leverages both cognitively inspired algorithmic insights and platform innovations to achieve Bayesian goal inference in faster than real time. And I'll now walk you through the details so you can see how all of this comes together. So first, the agent model. In general, we've seen that for an observer to infer an agent's goals, the observer needs to simulate how that agent would plan to achieve each plausible goal. How do we avoid this from becoming really expensive? Right. Our key insight is that if we can assume that agents are planning to achieve their goals online, then during inference, the observer only needs to plan ahead as much as the agent does, limiting the amount of computation they're performing at each step. Right. So this is illustrated on the right here. Here I'm showing an agent that doesn't form a complete plan before acting. Instead, guided by a search heuristic, it performs a partial plan, takes a number of steps, then replans before acting again. Right. So this is both cheaper than full horizon planning and also a more realistic model of how boundedly rational agents like ourselves, like humans, might actually plan. So it captures suboptimal behavior, like I'm showing here, where the agent optimistically tries to get close to the blue gem, but then realizes it actually needs to backtrack and get a second key. And it does that in order to finally reach its goal. But how do we actually implement this kind of agent model in a way that captures a wide range of planning behaviors, not just super suboptimal ones or not just really optimal ones? So here's where we leverage the flexibility of probabilistic programming, which allows us to mix probabilistic code with planning algorithms, defining a rich probabilistic model over an agent's actions, right? So first we can write a program that defines the prior of the agent's goals. And here's just a simple one, can be uniform or something more complicated. And we're going to simulate a sample, in this case, selecting the blue gem as the possible goal. All right. And then in each step, we're going to simulate how the agent plans to achieve that goal, right? In particular, we're going to simulate whether the agent does additional planning at all at this time step. And if so, we sample a search budget for our planning algorithm, then run the planning algorithm until it reaches that search budget. So for example, SIPS is designed to use incremental planning algorithms like real-time heuristic search, anytime variant of the classic A-star search algorithm, to produce not just a partial plan, but a partial policy, right? A policy is a conditional plan, you can think of it that way, that says what to do at each state that you might encounter. And now, because we don't run the search to completion, this policy is just going to be a partial one, as you can see on the right. But this is fine because the agent can just continue planning in the future to fill out this policy whenever they need to. So you can see it doing additional planning for regions of the state space it hasn't planned for yet, right? And then finally, we're going to turn this policy into a distribution or likelihood function over actions. And specifically, we're going to compute a softmax or Boltzmann distribution from this policy's, bounded estimates of how good each action is. So it's not going to use the true value function or cost goal function here. It's going to use this sort of partially computed values that are optimistic estimates of how long it's going to take to reach the goal. Right, so by putting this through this softmax function is actually improving the model robustness because it assigns non-zero probability to noisy actions which may not be along the optimal path to the goal or even the sort of estimated optimal path to the goal. And this actually becomes a kind of generalization of the classic Boltzmann rational agent model, except our model is more realistic in that it accounts for potential bounded rationality and is also much more efficient to simulate from. Great. And with this model, we can now simulate many, many possible ways an agent might act over time. Right here, I'm showing you a couple. And because we use compiler-optimized planning algorithms from this PDDL-JL library I wrote, which are guided by domain general search heuristics, we can not only run agent simulations very rapidly, this is kind of, slower than the true speed, in fact, but over any domain specifiable in this planning domain definition language, right? So this ability is a key aspect of what makes SIPS, both general and highly efficient. So if you're a good Bayesian, you might be wondering how we can go from efficiently simulating agents to efficiently inferring their goals. You might be even wondering whether efficient inference is possible over such a complicated Bayesian model, right? Because after all, it seems like in my effort to make planning more tractable, to do this kind of bounded planning model instead, I went from a Bayesian model where there was a single latent goal that we were trying to infer to a model where there's also tons of latent partial plans that we're trying to do inference over. And so while the first tractability challenge may have been solved, it seems like we made the part of the second challenge harder. Right. So here's where we turn to sequential Monte Carlo or particle filtering. Rather than trying to do exact Bayesian inference over all possible goals and plans, SMC approximates the posterior distribution with a relatively small set of weighted particles, right? And as a sequential algorithm, SMC also allows us to exploit the step-by-step nature of online planning to perform step-by-step inference over the agent's plans and goals. Right. In fact, our model was specifically designed to enable this by using online planning algorithms like real-time heuristic search. And finally, SMC can be combined with fast bottom-up heuristics for generating goal hypotheses without compromising accuracy. And this is actually what's going to allow us to scale to environments with hundreds of possible goals. And I'll talk a bit about that in a bit. But first, let's see how that works. First, in a case where there's just this fixed number of goals, but many possible plans, right? So we're going to initialize these algorithms, in case you're not familiar with how particle filtering works, by sampling or enumerating a set of particles, right? So on the right here, I'm showing a collection of 9 particles or 9 hypotheses, with each row corresponding to one possible goal. So that's the red gem, that's the yellow gem, that's the blue one, right? And each cell is showing one possible plan the agent might try and take in the future to achieve that goal, right? You can see they're slightly different. And each particle is assigned a weight of 1 initially, and if you normalize that weight, you get the estimated probability, and that's shown as a bar on the top of each cell. Okay. So we then iterate over observed actions as we see the agent take actions over time. So, and as we do that for each particle, we're going to simulate how the agent is going to update its plan in every step, then update the particle's weight based on how well the plan explains the observation. So this step over here, you can look at the bottom right cell here. The bottom right particle predicts that the agent will follow a plan to the key in the middle, right? But when the agent doesn't actually follow that plan, what happens is that the particle gets downweighted because there's not a good explanation of the data that was actually observed, right? So the likelihood was low, and hence the posterior probability gets downweighted, right? This happens again when the agent is right next to the red gem. In that case, all these particles in the top, the red gem particles, they're going to predict, oh, the agent should move upwards if they're really going to try and collect the red gem. But that's not what happens, right? The agent instead moves to the right. And so all those red gem particles are going to get downweighted, right? Now, because many of our particles have very low weights, it doesn't really make sense to keep them around. So SIPS is also designed to do something that many SMC algorithms do, which is resample particles whenever the effective sample size drops too low. So after resampling, particles that had high weights get randomly copied many times, whereas the low weight particles are pruned, and all the resample particles are now given equal weights. And this allows SIPS to focus computational effort on more promising hypotheses, right? So this resampling step is going to happen a few more times whenever there's a prediction error large enough to downweight a bunch of samples. So in this case, there was a prediction error for those. So that we're going to do resampling again. Prediction error, I think, happens again when the agent suddenly does this weird thing. Those get resampled. Eventually, we're going to see that the agent is doing this thing where it's backtracking away from the yellow gem. And so the yellow gem particles are going to become very unlikely. This is going to trigger another resampling step. And now all our particles are blue gem particles, essentially. So our posterior approximation has converged on inferring, okay, it's almost certainly the case that the agent was trying to reach the blue gem here, which makes sense given the data we've seen, right? Cool. And along this way, we can basically output a posterior distribution over not just the plans, but over all the goals at the same time, right? So by marginalizing over that, you get this posterior distribution over goals. Cool. So conceptually, I think, what SMC is actually quite elegant. You can think of it as iteratively guessing and checking what the agent will do at each step, and then you throw away the bad hypotheses. But in practice, part of why these algorithms haven't been widely applied, especially in these kinds of settings, is that it's hard to get the implementation in the math right, especially for more complicated models. When you want to make a change to the model, you would used to have to sort of change the inference algorithm to accommodate the change of the model. And if you want to make a slight change to the inference algorithm, you kind of have to redo all of the math, right? But because we wrote this using a probabilistic programming language like gem particle filters, we're actually able to write the basic SIPS algorithm in just 3 lines of actual code. So here I'm showing more or less something that's pretty close to the actual Julia implementation in 3 lines of code, with all the low-level math automated for you. And that basic math will still be correct if that math will still be correct if you pass in a different configuration of the model that says, okay, maybe there's a different prior over goals. Or if you add in custom proposals or MCMC rejuvenation moves in order to improve inference. We'll see in just in a bit how this flexibility really helps us to scale to harder problems with hundreds of goals. But first, I want to show you how even this basic version of SIPS performs in practice. So here's what this kind of SIPS inferences look like in aggregate for the example we just went through. On the top right, you can see the probability of each goal, and on the map, you can see the inferred partial plans. And as you watch, you can see that SIPS actually makes reasonable goal inferences despite the agent's suboptimal behavior, and also manages to infer, in fact, that the agent is pursuing the suboptimal plan to the blue goal, blue gem, pretty early on, rather than pursuing the optimal plan to the blue goal, which would have involved picking up that first key first. And if we actually run this algorithm at full speed, and this is on a slightly different example, sorry for the change there, we're able to achieve, as promised, faster in real-time performance, about 30 actions per second when we use 10 samples per goal. I've actually recently gotten this, faster than that. And in fact, SIPS is faster by at least 2 orders of magnitude compared to a naive Boltzmann rational approach I described earlier, which fails to accurately infer goals even after tons of upfront computation because it's using, real exhaustive value iteration to really try and compute the value function over the entire state space, even though most of those states you never encounter them. Great. So SIPS isn't just fast, right? Because we don't always assume the agents are optimal. One other thing that's nice about it, it's more robust to mistakes that agents might make. So in this example, we have a case where it's easy to see, oh, I didn't mean to start that so soon. So it's easy for the agent to reach the yellow and blue gems, but it takes a bit of planning to reach the red gem. So can everyone see what you need to do to actually reach the red gem? Right, so you kind of need to go to the right and pick up those 2 keys there. Okay, but let's say I show you the agent do this other strange thing. You can I meant to play the animation, but what it does, it picks up the key, unlocks that left door, and then goes up there, right? So I think a lot of people watching this will infer that it was trying to get a red gem, but it got stuck. It didn't realize it didn't plan hard enough. And SIPS is able to make this kind of inference in the same way that humans very naturally make this inference. We ran a sort of cognitive science study on this, actually. And in contrast, a model that doesn't accommodate this kind of, bounded rational planning, the classic Boltzmann agent models don't account for this kind of bounded rational planning, end up inferring that, the only reachable gem is the only likely goal at this point, which is the yellow gem, because it must explain all mistakes as basically action level mistakes and not mistakes from not planning far ahead enough. So now what I've shown you is just a version of SIPS designed for fixed sets of possible goals. How do we actually scale to open-ended goal inference problems with hundreds of possible goals? So let's consider this block words domain as an example. If I play this animation, you can get a sense of how we humans might solve this task. So based on the letters that have been stacked so far, you're probably coming out with 1 or 2 bottom-up guesses about what word is being spelled, like ink or pink. But if it turns out your initial guesses didn't explain the subsequent actions, you'll quickly discard them, keeping only the good ones. And so this logic is essentially what we implemented in open-ended SIPS, an SMC algorithm that dynamically adds new goals to the particle collection based on actions observed, right? So at every step, to break this down, what we do is, sorry, I just need to find myself in my notes here. If I start, in every step, we propose entirely new hypotheses using some fast bottom-up heuristic, right? So if I start at this state over here, I'm showing on the right, I might propose goals like pink or link, because I saw I got stacked in K. But we're not just going to take these guesses for granted, right? When the next action happens, which is T getting stacked on top of P, we're going to reweight the guesses by the likelihood of that action, right? And this means that if we initially, guess a goal like pink by basically auto-completing the block tower we saw, that guess is going to get down-weighted, right? So I meant to show this next action. So if I saw T get stacked on top of P, that guess is going to get down-weighted. And that's because it would be irrational to stack T on P if pink were really the agent's goal. We're also going to propose a new set of particles by running the bottom-up heuristic again. In this case, nothing ends with T and P, so we're going to autocomplete the most likely block tower, which is still ink. And then we're going to re-weight those particles as well. And then we're going to resample our new and old guesses down to a smaller collection based on their relative weights. And this is the effect of tossing out the low weight guesses like pink. So like the basic version of SIPs, I think the intuition here is quite straightforward. You sort of like iteratively make new guesses based on some fast bottom-up, associations you have between, in this case, sub-goals that have already been achieved and the complete goals they might be associated with, right? That's a noisy heuristic that may not always be right. And you check them against a coherent model of how agents actually plan, but do that pretty rapidly because we're using SIPs. And this gives us a really nice way to scale these basic SIPs to a much larger space of possible goals, right? So, and just to show you here how it works, this is what we did in Bloxworth domain. The end results were able to accurately infer the agent's goals of just 10 Monte Carlo samples using an anagram language, a very small language model as their bottom-up proposal, an anagram language model over the characters and words. And just like the basic version of SIPs, we're able to do inference over all 169 goals in real time without compromising accuracy. In fact, open-ended SIPs matches or exceeds accuracy of both humans and exact Bayesian inference in this domain we tested, while running 12 to 85 times faster than exact inference, which actually tries to do inverse planning over like 800 possible goals in some cases. Note that its accuracy measures average across all time sets, which is why, including steps where there are only 1 or 2 actions taken, so which is why the best you can do here is only about 20%. It's still a lot better than, say, 1 over 800. And while it's still ongoing research, I'm currently working on ways to generalize open-ended SIPs to more domains like this kind of virtual home environment. For example, similar to methods like symbolic knowledge distillation, I'm exploring how we can distill efficient n-gram proposals from large language models so that we can infer a wide range of household activities, for example, with very low cost. So the idea here is like, where do you get these priors? Well, we kind of have them now with these language models, but we want them to be like much faster to call an inner loop of an algorithm than calling, 04 or whatever it is in the middle of these algorithms. And one way we can do that is by distilling the sort of necessary statistics for these kinds of tasks. And another thing I'm quite interested in is like there's a ton of interesting work in the traditional AI planning community that sort of makes planning easier by analyzing logical relationships between sub-goals and the goals they achieve. That can also be used for goal inference because once you see if you analyze that achieving a certain sub-goal enables achieving some future goal, that's a pretty good sign that for a way of generating, okay, this is maybe a good hypothesis to propose in the future, given that this sub-goal has been achieved now, right? So stay tuned for that research, hopefully in the future. Cool. So that's SIPs, which allows us to build AI systems rapidly and reliably to infer goals of agents from their actions, while staying robust to human planning mistakes and achieving open-ended goal inference over hundreds of possible goals. Oh, I meant to show that little summary, but there it is. And just to give credit where it's due, these are some of my wonderful collaborators that I worked with over the years on this topic. So I've shown you how we can scale up inverse planning. In cooperation, however, we don't just coordinate by inferring goals from actions. We also communicate with each other, giving instructions or requests that we expect others to understand and inferred intentions behind people's words. So in this section, I'll be talking about how we can integrate SIPs with large language models to become CLIPS, a system for Bayesian instruction following and goal assistance that's much more reliable than using large language models on their own. And to introduce the setting for CLIPS, I'm first going to introduce language augmented assistance games, an extension of the assistance game formalism, also known as cooperative inverse reinforcement learning, by Dylan Hatfield-Manel, Stuart Russell, and others, that formalizes what you might think of as ideal rationality for AI assistance, right? And this two-player Markov, at least for bounded tasks, at least, right? So in this two-player Markov game, there's a human who has an unknown goal, an assistive agent who has a prior over the human's goal, and both the human and assistant can take actions. And in our language augmented extension, the human also can communicate to the assistant with natural language utterances, you. So in order to help effectively, the assistant has to infer the human's goal from both their actions and their utterances. So as an example of this, imagine you're in your friend's kitchen. They place 3 plates on the table. They then ask you if you can get the forks and knives, right? And based on this, you can intuitively infer you should get 3 forks and 3 knives, even though your friend didn't specify the exact number. how can we solve these assistance games, right? In cooperative language guided inverse plan search, or CLIPS, we model people as not just having an unknown goal, but also a joint plan that involves both themselves and an assistant. And that they follow this plan by taking actions, but also communicate to the plan by giving instructions. So by inverting this model, we can infer what someone wants from both their actions and their words, right? And there's a bunch of related work here that this sort of model builds upon, like the Imagine We and Bayesian delegation that you can check out. So we already know how to model goal-directed actions using SIFs, but how do we model this distribution over instructions in natural language, right? That seems like hard part. What's a rational model of speech production here? Here's where we make use of large language models as likelihood functions in a kind of interestingly different way, right? So as we know, large language models can be viewed as probability distributions over text. And so we can use them not just to generate completions given some input prompt, but also to evaluate how likely a specific completion is given some input text, right? So if we can kind of teach an LLM with a few examples of how to generate an utterance given an intention that's represented in code, we can evaluate how likely an observed utterance is given a specific intention, right? And so in CLIPS, we do this by prompting a large language model with few short examples of how to translate formal commands like unlock you, key 1, drawer 1, into sentences in English or other natural languages, like can you unlock the door for me? And by including these examples in a prompt followed by command C, we can evaluate the likelihood of an observed utterance U given that command. And so if we had a prior over possible commands, we could apply Bayes' rule to infer commands from natural language. Right. But in CLIPS, we don't just want to infer these relatively low-level commands. We actually want to infer higher-level goals and plans. So how do we do that? This is where probabilistic programming comes in handy again. By embedding our call to the large language model inside of a probabilistic program, we can model the structured relationship between an agent's intentions and their utterances. Right? In particular, given a goal G, a plan pi produced by planning towards the goal, we model the agent as sampling a set of actions from that plan to communicate as a formal command. There are many aspects of my plan I might communicate to someone else, not all of them, right? And then this command then gets translated into natural language by a call to a large language model. And so if we condition on this observed piece of natural language or utterance, we can infer a distribution over not just the low-level commands, but also the high-level plans and goals, right? And because we wrote all of this in a probabilistic programming language, all the math we needed to do here is automated, despite the fact that we wrote a pretty complex program that combines, symbolic subroutines with probabilistic ones with neural subroutines. So that's how we can integrate large language models into a larger Bayesian architecture. And by doing that, we can solve instruction following tasks that large language models struggle to solve on their own. So here's one example of that kind of task, right? So here's an example where at the bottom of this scenario, there's a human agent who wants to collect one of 4 possible gems, the red, yellow, blue, or green gems. At the top, there's a robot assistant that a human can give instructions to. And in the first few time steps, the human walks upwards and to the left. And based on this, our CLIPS robot assistant is able to infer that human might be going for the red gem or possibly also the yellow gem, probably not the other 2 gems. But once the human gives the instruction, hey, can you pass me the red key, it becomes most likely that they're trying to reach the yellow gem, since that's the only gem to the left that's behind a red door, right? In this case, you need red keys to open red doors, blue keys to unlock blue doors. And by making these inferences, the CLIPS assistant can accurately resolve the ambiguity in the human's instruction, providing assistance by picking up red key number 2 instead of keys number 1 and 4, because that's the most efficient route to actually assisting the human. Yeah, right. And if you think about it, if the assistant can only heard the language, can you pass me the red key? It wouldn't have known which of the red keys, right? It needs to sort of disambiguate from context by doing rational inference from both instructions and actions here. And if it had only seen actions, it also wouldn't have gotten the right answer. Okay, what happens if we try to use a large, something close to state-of-the-art multimodal LLM again, instead by prompting it with all the relevant context? Well, at least right now, when we tested, GPT-4o in this example, and I tried this about 20 different times with different prompt formats, repeatedly gave the wrong answers. It also produced flawed reasoning, such as associating red keys with a red gem, suboptimal assistance that prioritizes the robot's costs over the humans, and perceptual hallucinations, such as, coming out of non-existent doors, right? And even with O1 Preview from OpenAI's new series of reasoning models, reliability is very poor. So 1 out of the 5 times I tried, which each attempt took about 1 minute in processing time, so nowhere near real time. Only 1 time did O1 get the answer right, partly right with reasonable explanation. The other 4 times it gave answers that were either partly or wholly wrong. And all of this is, again, something that we, if you really want reliable assistance, especially in these grounded contexts, I think that's not quite what these models are delivering right now. Right. In contrast, CLIPS achieves high accuracies across the 2 data sets we tested, taking the correct assistive actions in 97% of Dorsey and Keyes problems, while closely matching the judgment of humans when presented with the same problems. And we achieve this reliability despite using only a much smaller large language model. Here we use the old GPT-3 query model, which is only 6.7 billion parameters, as our likelihood function in CLIPS. And this is possible because Eclipse uses LLMs to model what they're uniquely good at, language, while leaving reasoning to sound algorithms based on model-based planning and probabilistic programming. It's not just aggregate accuracy that Eclipse is able to give us. Another thing that Eclipse gives is safety in the face of uncertainty, right? So because Eclipse is a Bayesian algorithm, the way we select assistive actions is actually by minimizing the expected costs of reaching the human's goal. And this results in conservative decision-making whenever there's too much uncertainty about what the goal is. So for example, consider this scenario where the human agent doesn't move at all and just says, hey, can you open a red door over there? And the problem is there are 2 red doors. And so if the assistant can't ask any clarifying questions, then there's irreducible uncertainty here about which gem the human probably wants, and hence which door the assistant should unlock. Yet if you think about it, there's a clear answer as to what the most helpful action is here, right? Once you account for the fact that keys are gone forever once they're used. Does anyone want to say, or well, I'll say it so to save some time. Door 3 is safer, right? Because it preserves access to both it preserves access to both the blue and green gems. And this is precisely the assistive plan that Eclipse produces because we're being Bayesian about things, right? And and that's because we are accurately uncertain between the blue and green gems. And in contrast, GPT-4V acts unsafely in this situation, is overconfident that the blue gem is the goal, and hence unsafely unlocks door 2 instead of door 3. In high-stakes scenarios, this lack of uncertainty awareness can lead to serious losses, highlighting the importance of Bayesian rational approaches like CLIPS. Great. Cool. So that's cooperative language-guided inverse plan search, which applies inverse planning not just for goal inference, but also for Bayesian instruction following, and achieves much higher reliability than state-of-the-art large language models, while providing safe assistance under uncertainty. And I want to thank my co-author here who did a lot of the work together with me, Lansing. Wouldn't have made it to publication without him. And I'll move on to the last bit of, I just want to show you, we've started getting a bit of this on, I guess, robots recently, and you can check out that paper if you'd like. So how can we continue scaling cooperative intelligence to sort of a wider setting than what I've considered so far, right? Or going back to the question I've started, how can we build AI that cooperates with humans as reliably, safely, and efficiently, at least as well as other humans do? Over the course of this talk, I've shown you part of the answer with SIPs, which scales inverse planning for goal inference by combining flexible probabilistic programs with high-performance model-based planners. I then shown you how CLIPS builds upon this core capability, providing the basic architecture for a reliable AI assistant that's both capable of cooperative decision-making and cooperative communication. So what else is needed to turn CLIPS into an AI copilot or, say, a video game NPC as a sort of use case that's ready for deployment? And how can the technologies I've presented here enable cooperation not just between single agents and their users, but also infrastructure for cooperation at the societal scale? Well, starting with just cooperative agents like copilots, NPCs, and cobots, I believe we're actually on track to creating such systems using the rational model-based approaches I presented here in the next 1 or 2 years, delivering much higher reliability and lower costs than large-scale end-to-end methods. And I'm not thinking that we can do this for a lot of tasks where we don't already have, say, like a rational theory of how to achieve them. But it turns out that I think for many of the tasks we actually care about, like, web agents, web browsing agents, or like, agents that interact with a user in a video game world, we kind of have all the necessary ingredients, right? We kind of have already a lot of the modeling infrastructure we need to build, symbolic models of the world to do planning and inverse planning in. And, and we kind of have a good theory of how to create good behavior in those situations, which is, forward search-based, model-based planning, right? Um, so, for example, it's not imagined hard taking a scripting API exposed by a game like Minecraft, use it to synthesize a simplified domain model suitable for planning and inverse planning. In fact, people have already tried doing versions of this, like in the paper I'm showing here, where to use large language models to help generate these symbolic world models. You can imagine building AI agents that use that to infer what humans are doing in the environment and also plan to achieve goals for humans once it's given some kind of instruction. And I would argue that this is actually much cheaper than the alternative that some people are trying, as example by, Google DeepMind's scalable, instructable multi-world agent. They trained this thing on 1.2 million training steps on many different video games just from pixels alone, I guess, to directly follow instructions in video games. And, while they are able to follow simple instructions like chop down a tree or drive the car, really the success rate was 50% of the time for most instructions. And I just imagine that the computational cost of actually getting these things running in many systems is going to be way more than you can actually fit on, say, consumer hardware, right? So that I don't see happening in the near term. It's like not going to be economically scale. Or consider how clips could be applied to something like Microsoft Excel, right? While it's a large and complicated application, it's also one of the clearly defined space for actions or in fact for most basic uses. You go to cells and enter text or want to finitely many formulae, or you're sorting and filtering columns. So it's not hard to imagine building a clips-like assistive agent on top, which infers what you're trying to do from both your recent actions and your chat instructions, right? And in contrast, if you ever try to use Copilot for Excel, I've tried to use it a couple of times, you'll find that it's not very intuitive. I haven't tried it very recently, but that was my experience when I did try it. It definitely isn't able to infer what you're trying to do from your recent actions. It just has the work of the chat. And it often ends up being slower than getting things done yourself, right? So I think of the right kind of modeling infrastructure, clips in Excel or other kinds of assistive agents for these kinds of, digital worlds are going to actually work a lot better. So that's one piece of platform infrastructure. I think that will help us build model-based copilots. How can we actually build systems that have concrete these symbolic models of the world, not just for these PDDL domains I've been showing you, which have been applied in robotics, but also for say video games and also for web browsing tasks, maybe even like operating system style tasks, right? I think that's a really interesting and open research question that we have to address and something I'm hoping to do as one of my many research directions going forwards. But there are also many other cooperative capabilities that we'll have to develop out. So I'll just flash a few here because I know we're running out of time. Grounded task dialogue is one of the ones that I'm kind of most interested in, and many other things, inferring beliefs. So I'm going to skip through many things here. So grounded task dialogue. So I think I've shown you a little bit on how we can do reliable instruction following, right? Which is just like interpreting what someone wants from what they say under uncertainty about what they actually want. But we also want to do other things, right? A good assistant should communicate back, right? So in a situation like this, you would really want an assistant that asks clarifying questions like, do you mean door 2 or door 3, right? Or say things like, there are actually 2 doors, informing the user of things they might not actually know. So how do we build systems that can do that in a reliable way as well? Here is where I think we can combine the strengths of probabilistic programming and large language models again, using some recent work that I've been working on with some of my collaborators for constrained generation of large language models. And it turns out that same techniques we can use for Bayesian inference, sequential Monte Carlo, be used for Bayesian goal inference, can actually be used to steer or constrain the generations of large language models as well, right? And the reason you can do this is because you can think of many constraint generation problems as posterior inference problems, right? So let's say you want to impose a hard constraint on what a large language model says. That's like saying, okay, constrain the distribution of over strings subject to all words having less than 5 characters, or all words lying in the syntax of Python, or something like that, right? Or infilling is another constraint generation problem. It's essentially a posterior inference problem. And even classifier guidance or reward-based steering can be viewed as kind of like soft constraints on the giving you a different kind of target distribution or posterior distribution you're trying to sample language from. How is this useful for grounded task dialogue? Well, if you recall from CLIS, parsing utterances can itself be viewed as a kind of posterior inference problem. You're trying to infer a formal command from some natural language utterance, upweighting commands that assign high likelihood to the utterance. and have higher prior probability while enforcing a syntax constraint. And while in the original version of Clips, we solved this posterior inference problem by exact enumeration, that's just not going to scale. And you can instead use SMC to sample from this posterior distribution or instead, so you can actually scale to a much larger space of possible intentions that a person might have. And similarly, I think generating utterances or questions can be framed as posterior inference as well, right? So instead of just directly translating a desired command into an utterance with the language model, you can imagine using SMC to generate a string that has high likelihood of being interpreted correctly by a listener as intended command, assuming you have a good model of how the listener would interpret things, right? And alternatively, we can generate questions that are designed to be informative when answered by adding a term proportional to expected information gain to sort of steer generations of the language model that way. And I think by doing this, we can basically enforce LLMs to be cooperative speakers and listeners in the style of some of you might have heard of rational speech act theory, allowing our agents to be helpful and informative communicators kind of by design rather than just by training. Great. So there's a lot more I could say about how we can scale capabilities for specific agentic applications. I want to close off by discussing infrastructure for AI and human AI cooperation at a grander societal scale. Because while humans are one of the most cooperatively intelligent species on the planet, we're also one of the most likely to have disastrous conflict with each other. And just getting AI systems to be more cooperative with their human owners isn't going to solve their problem. If anything, it might make things worse because of AI-enabled human conflict. And to address this challenge, we'll have a scale-up cooperation in the setting where agents' interests aren't fully aligned with each other, whether that's humans or the AI they control. Right? And I've already started doing some of this research together with my master's student, Ninel Oldenburg. Right? In particular, we were interested in designing agents that learn cooperative norms from the agents around them, because that's one way humans manage to avoid mutually destructive outcomes. And while the environment we use here isn't very realistic, it's kind of a microcosm of the issues that humans run into, like depletable food resources, pollution that harms resource growth. If agents in this environment fail to cooperate to prevent freeloading, they can easily end up destroying the environment like this RIT agent is actually doing here, because it doesn't know the rules that society is following in this context, right? And so to address this, we actually extended the idea of inverse planning in SIPs and Clips to Bayesian norm learning and Markov games, right? So the way to think of this is that just as Clips agent infer a shared goal that both the user and the assistant has in order to assist the users, we design agents that infer shared norms or shared rules that other agents in their society follow, right? Because just by watching what other people do and don't do, I should be able to infer something about a rule society follows, right? For example, if I normally expect you to eat apples because it's in your interest, in your self-interest anyway, but you instead go narrow self-interest anyway, but you instead go and clean the river, I should maybe infer there's a social norm at play. And by modeling norm learning in this way, we were actually able to unify several different technical literatures and social norms. I won't go into detail here. And we're also able to build agents that rapidly acquire cooperative norms, avoiding the negative outcomes I showed earlier. And this is actually much faster than you would achieve it with like, multi-agent RL, which takes like 6 to 7 orders of magnitude more of training experience. Of course, being able to learn social norms is just one small part of cooperative AI infrastructure. We'll also need to figure out better ways of having humans and AI deliberate on good norms, and of establishing mechanisms and institutions that allow humans and AI to cooperate at scale, drawing on ideas from game theory, social choice, and elsewhere. So there's a lot of work to be done, which I plan to pursue in the future. But if we do the work and get it right, I think we can stand to benefit from a safer, more cooperative, and ultimately more fulfilling world, one where AI isn't a pathway to our demise, but instead to a world where we can live and flourish together despite all of our differences, right? And with that, I just want to say again that I am starting as an assistant professor in US this fall very soon. I am recruiting PhD students. If you know anyone, if you yourself are interested, feel free to reach out. Here is a summary of the talk. I want to thank my advisors, thank a lot of other people, and thank you for your attention. I know we are almost at time. Thanks.
Well, thank you so much for this excellent talk. Yeah, we have perhaps like 3-4 minutes for questions. Any questions from the group? If so, I think we can
yeah, I think Aiden has
yes.
Yeah, thanks. And great talk, by the way. I'm curious about like how this sort of goal inference thing can be extended to cases where people act against their interests in like sort of a longer term. Like I saw that already accounted for some irrationality, but I think like in economics, when you try to like just sort of assume people are doing what they care about, often that's like not very good. So like, how do
No,
you
yeah, I think totally. So I think, again, rational in the sort of, I mean it rational in sort of more basic or weak sense, right? Not kind of like strong rationality. And I think it's totally right that, humans, we're bounded creatures and we don't always fully realize their short-term goals might sort of fail to correspond with that. So I think part of the sort of thing I showed earlier, where we actually have a model of boundedly rational humans, can be extended to this idea, I think, of like what happens when people don't select short-term goals, which might not actually comply with their own sense of like what is in their best interests. And that's something, happy to talk more about how you could actually do that. I mean, if you had a model of how high-level goals get turned into low-level goals, and some model of like how errors occur in the process due to sort of like, time discounting or whatever, that's one way you can kind of correct for those kinds of issues, essentially. And I think there's another question about how to assist in that context without coming off as really paternalistic as well. Yeah.
Yeah, I mean, I really liked the norms work at the end there, and I feel like that
Thanks.
kind of ties into figuring out basically like what's best for humans outside of their self-reflective, potentially deceptive goals. So yeah, I think that's a really cool direction of these like sort of implicit goals that exist outside of individual agents.
Yeah.
That was really cool. I liked a lot of that. Especially the experiment with when you first introduced like the LLMs kind of I don't know exactly at what point, but when the LLMs, like when you introduce language into the goal framework, and it had, I mean, and even the following examples, like it was so high performing at predicting things correctly when given the language. For in your first example, like it was 100% certain that
Yeah, I'm not sure whether it should have been
yellow.
as certain as it was, but like yes, it definitely was quite certain. And I think something going forward is like how can we actually, I think it worked quite well in that domain. I think partly it was designed to really show the differences. Like, I think part of the methodology I've used in a lot of my research is kind of inspired by cognitive science, like finding key examples that kind of show off like, okay, humans can do this, and like really we should build AI systems that can. That's a bit different from, I think, traditional machine learning methodology. And I think one thing I want to do is like keep making sure we can maintain those core capabilities, but also scale to like more realistic settings in much wider scenarios. Yeah.
Like I was wondering if you noticed any weak spots or theorized any weak spots for this kind of.
Oh, there are definitely failure modes, and I think there are sort of interesting things I learned from doing many of these projects that I was like, oh, that's interesting. You can change the model in this way. I think one thing that's nice about taking these sort of explicit modeling approaches is that you can quite clearly see where the mistakes arise due to your modeling assumptions being wrong. Part of it can be inference going wrong, but I think if you get inference well enough, then you can sort of think, okay, it's actually the model is misspecified in some important way. And so there are some interesting cases in a cooperative setting. I've realized that our model actually assumed that humans were a bit too rational than they actually are. And I think a model of more hierarchical versions of cooperative planning where people sort of separate out sub-goals to each agent, and then that each agent pursues those sub-goals independently is actually, for a bunch of reasons, more robust than what we actually initially ended up implementing.
Cool.
Awesome. I think for the interest of time, we'll wrap it now. But again, thank you so much for this awesome presentation. And also thank you everyone for attending.
Yeah, thank you all for inviting me and being here.